In this session, we will discuss the concept of internal energy in thermodynamics in a bit detail. So you know that the potential and kinetic energies is considered both in mechanics and thermodynamics. So if these energies result from the position and motion of the system as a whole, then they are usually regarded as external energy of the system. So if potential energy and kinetic energy result from the state, or I can say position or motion of the system, any system under consideration, system as a whole, then these energies they are regarded as external energy of the system. That is what we usually consider in mechanics. In mechanics, we are bothered about the motion of the system as a whole, or the state of the system as a whole. We are least bothered about what happens to the internal constants of the system. So the sum of the kinetic and potential energy is a measure of the external energy of the system. But in the case of thermodynamics, we are actually not considering the external energy or its contribution. Instead, we are concerned about the total energy of the constituent particles which make up the system. Okay, so it's purely the energy which is internal to the system, and hence we name that as internal energy of a system. Hope you can follow the thing. So the sum of Ke and P, kinetic energy and potential energy of the constituent particles of a system, okay, means which is purely internal, internal because it is connected to the internal constants of the system, which is purely internal in nature, or I can say intrinsic nature, is called the internal energy of a thermodynamic system, of the thermodynamic system. So it should be just made well and clear that while we calculate or while we measure the internal energy of the system, the energy gained by the system by the motion of the system as a whole should not be taken into consideration. For example, suppose that you have got a container of gas maintained at a particular temperature. If you are lifting the container as a whole, the container of gas as a whole, say by a height h, I am lifting the container as a whole by a height h, then the potential energy of the container of the gas changes by mgh. Okay, but this work has been done on the system as a whole. It has changed its potential energy as a whole, but we do not count this work done as what is known as the internal energy of the system. That is purely external. Similarly, if you are keeping this cylinder in a moving truck, say you are keeping this cylinder in a moving truck which is moving with a velocity v, then along with the truck, the cylinder also has got a kinetic energy which is equal to half mv square, right? And this kinetic energy is also external as per our definition. So we should not count these types of energy which are external with the energy that we are considering in thermodynamics. So that is something very, very significant thing. So we define the internal energy of a system in thermodynamics as the sum of the kinetic and potential energies of the system which are contributed only by the constant particles of the system. Means either due to the motion of the constant particles or by the interaction between the constant particles between themselves. So that is something to be kept in mind. So one word of caution. So we will just write internal energy U denoted as U is equal to Ke plus Pe, right? Both are internal energies, Ke plus Pe, where I told you the Ke can be due to the motion of the constant particles. Now this Ke can have several contributions actually. If you go to the molecular dynamics, you will see that the Ke can be due to the translational motion of the molecules. So I can say there is a translational kinetic energy or translational part of the kinetic energy. It can be due to the rotational motion of the thing. You have learned about rotational kinetic energy, something like half I omega square. So if the particles are not monoatomic, if the molecules are some diatomic or polyatomic, then you can say that there will be some kinetic energy due to rotation. So there is Ke due to rotation. You will see that there will be something like Ke due to the vibration. Okay, so the bond which connects two atoms in a molecule can stretch or it can get compressed. So there will be some sort of a vibrational motion. You have learned about the energy associated with vibrational motion. So there can be kinetic energy to vibration, etc. So remember, there can be different contributions to the kinetic energy of a system. Can be due to translation, can be due to the rotation motion, can be due to vibration motion, and maybe you will see that these different kinds of kinetic energy will not be available at all temperatures. Certainly there is some sort of a temperature dependence for these terms. You will learn about that one later. There is what is known as degree of freedom of the system, and only at very high temperatures sometimes you can see motion such as vibrational motion, etc. will be getting excited. Anyway, for the time being, you remember that the internal energy of a system will have usually two terms. In general, two terms. So a kinetic energy contribution and there will be a potential energy contribution, and the potential energy contribution is purely due to the interaction between the atoms. And hope you remember one statement that you have learned. In the case of ideal gas, this potential energy contribution is considered to be zero, because we consider the ideal gas atoms or molecules to be non-interacting. So the internal energy is purely kinetic in the case of an ideal gas. Now there is a very important concept that is associated with the internal energy of a system. I can relate the internal energy of a system with a type of work what is known as adiabatic work. So that is our next aim. So the connection between internal energy of a system, internal energy, and adiabatic work. So we have seen that in general, work done in thermodynamics is considered to be path dependent. We have proved it before. So here we will see an exemption to that general statement. So we will connect internal energy of a system with the adiabatic work done on the system or by the system. So let me take you to the case of work done in mechanics in general. You consider the work done against or by a conservative force. In mechanics I am talking work done by or against a conservative force. You know several examples of conservative force. The most common examples are gravitational force. Example, you can take gravitational force. Hope you remember that the work done in gravitational field or work done by or against gravitational force is actually path independent. It's not W is path independent. Hope you remember this statement. Path independent. And that is why we called it as, that was the criteria for calling a force as conservative, path independent work. Okay, so the meaning is that you have got a lower state and there is a higher state. Maybe it is the 2 stories of a building. Now I have got a mass M here with me. Suppose the height between the 2 places be h directly. Now if I lift this mass straight up by height h so that it reaches here, we will say that the mass has now gained a potential energy is equal to mgh, which is nothing but the work done in lifting the mass against the gravitational force, you know. Okay, so P equal to mgh, you know, work done is now converted into the potential energy here. Now suppose that I just move the mass like this to the side. Then I just so I have moved by a distance here, say then I lift it to the same position. You will see that in this case also the work done against gravity is still equal to mgh, or the potential energy remains mgh itself. Or if I lift it to the side, then I just move it up a bit, okay, by some height h1. Then again I move it to this side, by some distance, and then again I reach back to the same height. Suppose it is reaching back here, so that this is h2, such that h1 plus h2 equal to h. In the third case also the work done, which will be equal to the final potential energy, is equal to mgh. So you can see that the work done by or against a gravitational force is independent of the path followed. Instead it depends on the only on the initial and the final positions. Hence you can see that in such cases we are defining what is known as a potential energy function. In the case of conservative forces, we can always define what is known as a potential energy function, which we usually denote by U. Hope remember, this is the basic idea in mechanics. Whenever there is a potential energy or whenever there is a work done which is independent of the path followed, we can define an energy function which we usually call as a potential energy function. Same thing we have done in the case of electrostatic force also. If you remember, you can just recall that one. That in the case of electrostatic force also, we have defined some sort of a potential energy function which depends only on the initial configuration of the system of charges and the final configuration of the system of charges. Okay, and hope you remember that the potential energy function in these cases are related to the initial and the final state. So it is a state function. The potential energy function is a state function. Okay, the same manner in thermodynamics, I just made a similarity with the idea of conservative forces in mechanics. In the same manner in thermodynamics, it has been experimentally observed, or it has been empirically observed, that there exists a function in thermodynamics. There exists a function of thermodynamic coordinates. There exists a function of the thermodynamic coordinates means which all of the initial state and that of the final states, thermodynamic coordinates of a system. There exists a function of the thermodynamic coordinates of a system such that the change, or I can say whose final value minus initial value, the difference between its final value, I am going for a mathematical definition, final value and initial value, such that the difference between its final value and initial value equals the, this is something significant, the adiabatic work. See that I am specifying the kind of work here, adiabatic work in going from the initial to final state. So let's repeat this statement. This is something very conceptual. Empirically or experimentally, we have seen that in thermodynamics there exists a certain function of thermodynamic coordinates of the system such that its initial value and final value differ by an amount which is equal to the adiabatic work done in going from the initial to the final state. Or putting it in mathematical way, I can write the function here refers to internal energy function U. So I am writing the function is U. It has got a final value UF and has got an initial value UI, say. The function has got a final value UF and the function has got an initial value UI. So the difference between these two functions will be equal to the work done by or against the system, by or on the system. But what kind of work done? Work done can be isothermal, it can be isobaric, it can be isochoric, okay, which is equal to 0 of course, or it can be adiabatic. So the work done here in this case should be purely adiabatic. Okay, in going from I to F. So this is something which is important in thermodynamics, which defines the concept of internal energy as a state function. So internal energy is a state function. Internal energy is a state function which depends only on the initial and final states of the system. Moreover, you can understand one thing from this equation, that even though we defined the work done in thermodynamics to be path dependent in general, the adiabatic work done, by using this concept or definition of internal energy, we have seen the adiabatic work done is depending only on the final state and the initial state. So we can see that adiabatic work done is path independent. So W adia is path independent, and that is of course there is a difference that you have to keep in mind or note down. So there are two important concepts that have come out as a result of our discussion over here. One states that U is a state function, internal energy is a state function, means it does not depend upon the path. And another thing, even though in general work done in thermodynamics is path dependent, the work done which is purely adiabatic in nature, or by purely adiabatic means, is path independent. This is very similar to the concept of work done by or against a conservative force in mechanics. Remember the thing. So there are similarities there. Okay. So these ideas will take us to the first law of thermodynamics, which we will see will be connecting the work with the internal energy. We will discuss the first law of thermodynamics in the next session. Thank you.